Now, sketching a function like this sometimes produces some unexpected results, but the more of these you graph, the more you're likely to spot some patterns and recognize things straight away. Now, rather than throw the entire curve sketching menu at this, I want to look at things that are familiar and have them jump out at me so I can think about them. I know the line y equals x is really straightforward, looks like this. I also know that the graph of y equals sine of x looks something like this. Goes through 2 pi, it's got intercepts every pi, looks something like that. So if I'm finding any y value on this curve, I need to take the y value that would correspond with this graph and add on the y value that would correspond with this graph. So it's going to have this basic shape, isn't it? Because all the y values on this curve, y is always between 1 and minus 1. That's all it will ever be. Whereas the y values on this curve are always exactly the same as the x value. So as x gets bigger and bigger, y is going to get bigger and bigger, but it's always going to deviate going up and down this line. So a good guess, before we even start, would be that it's going to follow something of this pattern, but it's also going to follow it heading upwards in that direction. Now, the easiest way to graph this would probably be to just find some key points. So start with your intercepts. When x equals 0, what's y? Well, we've got 0 plus the sine of 0, and that's 0. So it's 0. So this thing starts by going through the origin. So let's start graphing it, and we've got something to go with. Now, are there going to be any other x-intercepts? Well, if you let y equal 0, then you're going to have 0 equals x plus the sine of x. And subtracting one of these things from both sides, let's say the sine of x is equal to minus x. Now, we know that the sine of x has to always, just like this, has to always be between negative 1 and 1. It can't get up to 100 or minus 100 or any other big numbers in either direction. So for the sine of x to equal negative x, the only answer that fits that is 0, 0. So we've only got one intercept in either direction, and that's the origin. Now, let's use our calculus to see if we can find any stationary points or flat spots on the curve. This should be quite easy to differentiate. Y dash equals, one part at a time, we get 1 plus cos x. So if we want to find any stationary points or flat spots, we need to let y dash equal 0. So then we get 0 equals 1 plus cos of x. So cos of x must equal minus 1. Now, we know what the cos curve looks like. It equals minus 1 quite often, doesn't it? And coming up with a pattern is a great idea right now because it gives us multiple answers really quickly as soon as we spot those patterns. So here we've got 2 pi, it comes back up again at 4 pi. So finding when cos of x is equal to negative 1, well, it equals negative 1 exactly halfway along its period, doesn't it? And that's at pi. And then it would do it again another halfway along the next period, which would be 3 pi. And then it would go again at 5 pi. Now, we haven't been told the domain that we want to graph this over, so it makes sense to just spot patterns so that we can see what's going to happen over and over again. I can see here we've got pi, 3 pi, 5 pi, dot, dot, dot. Now, these are going to be stationary points. What type of stationary points are there? Are they? Well, to check, we can find the second derivative, and we can sub in these values. And if it's a negative, we'll know it's concave down. If it's positive, it'll be concave up. And if it's 0, we'll have no concavity at all. It will actually be a horizontal point of inflection. So let's go ahead and do that. Let's find the second derivative. When we differentiate 1, we get nothing. When we differentiate cos x, we get minus sine x. So this is nice and straightforward. Now we can ask ourselves, when x equals all of these things, what would the second derivative be? Now, I'm going to put it into a table rather than say when x equals this, double derivatives that, when it's this. Otherwise, I'll be there all day. So let's make ourselves a little table here. All right, when x equals pi, 3 pi, 5 pi, etc., what is the negative sine of those angles? Well, let's go back to our sine curve. The sine of pi is 0. So negative 0, that's just 0. The sine of 3 pi, well, if I kept this curve going on a little bit further, I know that 3 pi is another place where it touches down on the x-axis. In fact, it has x-intercepts at pi, 2 pi, 3 pi, 4 pi, etc., etc. So when x is 3 pi, sine of x is negative 0 again, or just 0, and this pattern is going to keep coming. Now, what does this mean? Well, a concavity of 0 is actually a point of inflection, potentially. So if we've found that these are flat spots, but they're also points of inflection, therefore they are horizontal points of inflection at these points, pi, 3 pi, and so on. Now let's put some things on our graph. If we have pi, 2 pi, 3 pi, 4 pi, what we're saying is that we have flat spots at pi, 3 pi, all the odd ones. So here, here, here. Now we're expecting our graph to go up somehow with a sort of wavy line. That's what we predicted from the combination of the two graphs. We've got some flat spots. We know that they're horizontal points of inflection, but are there more points of inflection than just these? Well, to look for points of inflection, let's let the second derivative equal 0. We looked at what the second derivative was at particular values of x, but perhaps there's some more points of inflection that we haven't considered. All right, the second derivative is minus sine x, and we want to let that equal 0. That's the same thing as saying sine of x equals 0, isn't it? Because the negative there is not really doing anything. If something equals 0, it's 0. All right, we want to know what values of x have the sign of 0. Well, we've already considered it, pi, 2 pi, 3 pi, 4 pi, etc. And what that means is that we've got a potential point of inflection every pi. Now, how do we check it? Well, we started here by making our little graph showing x values and what the second derivative was. We need to extend this table out. We need more in it, because other than just pi, 3 pi, 5 pi, etc., we now want to check 2 pi and 4 pi and all of those, and we need to check for a change in concavity in between each one. So now I'm going to do a little table. I'm using a bit of my space here, but I sort of need to on the board so you can see what's happening. Let's look at the second derivative at a bunch of points. How many points? Well, enough that we can see a pattern. So let's go 0, pi, 2 pi, 3 pi. That's probably enough. And we've seen that the second derivative is actually 0 in all of those places. But what we want to do is look at the concavity of the curve in between. Because if there is a change in concavity, then these are all points of inflections, and we need to check that. So let's go pi on 2, 3 pi on 2, 5 pi on 2, etc. All right, now what we're looking for then, if the second derivative is, where is it? Here. We want to know the negative sine of each of these angles. All right, having our sine curve right here is really helpful. The sine of 90 degrees, or pi on 2, that's here, and it is 1. So I've got negative 1. All right, 3 pi on 2, that's over here. The sine of that is negative 1, so I've got negative 1, that's positive 1. All right, the sine of 5 pi on 2, well, that's going to be exactly the same as pi on 2, because 5 pi on 2 is here, and we're at the same point on the curve as this one. So we're going to get the same answer, minus 1. And this looks now like a pattern. And if I was to look at the next one, 7 pi on 2, I'm going to get a 1. So what I've got here is some proof that all of these points, pi, 2 pi, 3 pi, etc., are all points of inflection. Now, only some of them are horizontal points of inflection, the odd ones. And we know that because they are the flat spots. Now, how does it start? We're starting down here at the origin, or at least as we go in this direction. We could continue it on once we've got our pattern. We want to start with no concavity at all. But straight away, when we've got pi on 2, this section is concave down. So that means it's curving this way. But by the time we get to pi, we've got a flat spot. So if we want to draw a little flat spot there, and think about making concave down between those 2 points, there we have it. Our next flat spot will be at 3 pi, which is up here, and it's going to be up much further. My graph's actually needing to go where that working is now, so I'll just rub that out, but you should already have it down. So we've got another flat spot up here. And at 5 pi, we have another flat spot. And in between, well, we've got another point of inflection here. So that's where it must stop curving concave up and start curving concave down. So this will be a point of inflection here that's not horizontal, whereas these points of inflection are horizontal. Our next point, we need to curve concave up, and then after it gets to 4 pi, concave down. So we end up with basically a wavy line that's going up and up like this, and it's curving itself around the line y equals x. Now, if you're wondering, how did I know that these flat spots needed to keep coming up? Well, a quick little table of values with x and y would tell you. I sort of did that in my head. I thought if x is pi, or 3 pi, because these are the flat spots I drew, or 5 pi, etc., what will y be? Well, y will be pi plus the sine of pi. What's the sine of pi? Nothing. So it'll just be pi. So I can see that if we've got pi across, pi up, it's like the line y equals x. There's a gradient of 1 between those 2 points. Up here, y will be 3 pi plus the sine of 3 pi. What's the sine of 3 pi? Nothing. So here we literally have all of these points, any point that we care to make here, all these flat spots, they're going up with a gradient of 1. Then we have our flat points of inflection, where we change from curving concave down to concave up. And in between, on the 2 pi and the 4 pi, all the even ones, we have a point of inflection that's not horizontal, and you can see it changes from concave up to concave down on those points. Now, quite a lot of work was done here to get this shape, but once you start seeing that graphs like this pop up quite often, you'll get better at realising that we're kind of combining the shape of each graph.